Hello and welcome to the 22nd lecture. So we're going to be talking about L'Hopital's rule, which we're going to abbreviate to L-Hop's rule. Okay, so what is this about? We all sometimes want to find out about this following kind of limit. The limit as x goes to a of f of x over g of x, where the limit as x goes to a of f of x equals 0, and the limit as x goes to a g of x is equal to 0. And this is kind of a fight, right? Because it depends on which guy tends to its limit first. So, or which guy tends to its limit faster. So if f of x is tending to 0 faster than g of x, then the thing on the top will be a lot smaller than the thing on the bottom as x goes to 0, and we expect an answer like 0. Conversely, if g of x is tending to 0 faster than f of x, and the thing on the bottom is going to be much smaller than the thing on the top, and that thing will be either a large number or infinity. So, for example, if we have f of x is equal to x squared, and g of x is equal to x, and a is equal to 0, then we have these conditions are satisfied, right? And the limit as x goes to 0, f of x over g of x is just going to be the limit as x goes to 0 of x, which is 0. Or what if we have f of x is equal to x, and g of x is equal to x to the power 3, again, and a is 0, then this limit goes to 0, f of x over g of x is going to be the limit as x goes to 0, 1 over x squared, which is equal to infinity. So again, the limit doesn't exist, because when we say the limit exists, we mean as a number. Nevertheless, we write the limit is equal to infinity, because there is an answer we can give, and that answer is infinity. So they're completely different answers based on the speed at which these various guys, f and g, tend towards their limit, right? Or we could have f is equal to x and g is equal to x, and then the quotient is just 1, and then the limit is 1. Right? So this is the kind of thing we have to find a tool to analyze to be able to answer these questions, because none of our original methods are going to work. We can't apply the quotient rule for products, the correct quotient rule for limits, because the bottom limit of this thing is 0. Right? So L'Hopital's rule is a tool that allows us to actually answer this question, and I'm going to state it, the simplest form of it right now, and then I'll explain the slightly more general forms. So, L-Hop's rule. Suppose we have these conditions. Suppose we have this, call this thing star, and G satisfies star, then the limit as x tends to 0, x tends to a, f of x over g of x is equal to the limit as x tends to a of f prime of x over g prime of x, if this limit exists. Okay? And it is also the case if we have that the limit as x tends to a, f of x, is the same as the limit as x tends to a, g of x is infinity, then the same thing is true. Then the same then also holds. And I'll show you after I'll show you in a couple of minutes why this thing is actually no great extra step. It's basically the same as this thing, but we'll come to that second. After we've talked about other things. All right, so when you first see L'Hopital's rule, you'll kind of think, well, this looks really sort of like a magic trick here. Why can't we just replace this problem by this problem? They look like quite different things. They're going to be different functions. And indeed, it seems a bit mysterious, but as always, it's not mysterious, it's just pictures. And we're going to discuss a special case of this that the entire thing can be reduced to, that kind of clarifies the situation. So consider this special case. So where we have that f of 0 equals g of 0 equals 0, and that f and g are differentiable near 0, and this is something you don't know, but that doesn't imply that the derivatives are continuous, but we're going to assume they're continuous. Don't worry about that if that's not something that seems worth saying to you. It's just for completeness. All the examples you will encounter where the derivatives exist, they will be, wherever they exist on their domain, they will be continuous, but that doesn't always have to be the case. So, and f prime, g prime are continuous. Near 0. So this in particular is the simplifying assumption that I'm adding here. Okay, so suppose we have this situation. Then let's draw a picture. So suppose this is the function f. And then suppose this is the function g. Okay, and we are trying to understand this thing. Okay, and we see that both f and g tend to 0 as x tends to 0. That's the assumptions, right? And the rate at which they go to 0 is actually the thing that determines what this answer is. And so what we're really looking at is something really close to the behavior around 0, and the natural thing to do is to take a tangent line and look at that instead. So if we take the tangent line to g, let's call that tangent line t, and if we take the tangent line to f, let's call that tangent line s. Okay? Then these tangent lines are pretty easy to figure out, right? Because we have a differentiable function. We're going through this point 0, 0. So notice that t of x is just this linear function going through 0. So it's just going to be determined by its slope, which is determined by the derivative of g at 0. So it's just given like this. And s of x is f prime of 0 of x, right? And we also know, because that is what having a tangent line means, that's what comes from differentiability, we discussed this in an earlier lecture, that if we take some small x here and we look at the difference between the tangent line and the function, which will be like this little quantity right here, this thing is very, very small compared to x. So as x gets smaller, this thing gets smaller as well, but it is a lot smaller than x itself. That's the meaning, that's the point of differentiability. Same for here, the difference between the tangent line and the function is way smaller than x. Yeah, and we can see it on the picture, and that's what we know. And in those lectures, when I talked about that, I used the following notation. So we know that f of x is like its tangent line, which is s of x, and then some very small error, which is this quantity right here, right? And it is way, way smaller than x, and that's the important thing about it. And I denote that by little o of x, okay? So I put a plus minus just to indicate it's some sort of an error, where little o of x is a lot smaller than x. And the same thing for g. It's equal to its tangent line. And it's a different error, but we're not going to give it a different name because we don't care, because the only thing about it that's important is that it's a lot smaller than x. So if we look at this thing that we're trying to understand, f of x over g of x, that is like s of x, the tangent line, plus minus this little error over this thing. And we know what s of x is. It's given by this thing, f prime of 0 times x plus minus little order of x, plus minus little order of x, right? And then we divide both top and bottom by x. Let's put it here. Yeah, because we're taking the limit as x goes to 0, so x actually is not equal to 0. Yeah, and we know that little order of x over x is incredibly small, goes to 0 as x goes to 0. That is the main property of little order of x. Yeah, so this expression is just going to tend to the expression f prime of 0 over g prime of 0. Yeah, so in the language of maths, that is that this thing, which we call question mark, now let's call this star star. So star star, in this special case, is just given by f prime of 0 over g prime of 0. Yeah, and since the derivatives are continuous, that's just the same as the limit of x goes to 0 of f prime of x over g prime of x, if this limit exists. Okay, which is exactly the thing that we claimed in the statement of the theorem, right? That is what we claimed over here. Okay, so all that stuff here is just the language of math expressing this picture. And what this picture shows us is that the rate at which g is tending out to 0 is essentially determined by the rate at which h goes to 0. Start again. The rate at which t goes to 0, right? It's tangent line, as we can see, because g is more and more like t as we get closer and closer to 0. And the rate at which f goes to 0 is incredibly well determined by the rate at which s goes to 0. So when we're looking at f over g, morally we can just replace that question by s over t, and that's what we've done here. So f over g gets replaced by s over t, and the little bit of an error we get from doing this is negligible as the limit as x tends to 0. Yeah, and that is just the fact that this little thing here and this little thing is way smaller than this thing, even though all of them are going to 0. Yeah, so because of this picture, it should be no surprise, it should make sense that when we are considering some sort of question about the rate at which things go to 0, then the issue or the thing that will determine that with the most relevance is the rate is the behavior of the derivative around that point that we're considering. In this case, the point A is going to be 0. Yeah? So it shouldn't be, after this picture, such a surprise that we replace this with f prime over g prime. Yeah? And we're going to see this as we discuss some specific examples. This is not an unnatural thing to do. Yeah, this is a reasonable thing to do. So that is why this thing holds true. It's not magic. It's not anything weird. It is not anything essentially more than this picture, right? And all this stuff is just more precisely describing what we see on this picture. Okay. I also promised to explain why we can consider the limits both being infinity, and it's just the fact that if we have both these limits are infinity, we can rewrite this situation like this. So if we have this assumption right here, then, I'm going to complete this box, then when we consider f over g of x, we can unwrap this as 1 over g of x over 1 over f of x. And if the limit as x tends to a of f is infinity, then 1 over f is going to tend to 0, and 1 over g is going to tend to 0. Yeah? So we're going to have the situation 0 over 0 in this case too. So essentially because of that, it shouldn't be a surprise that we can deal with this case too. It can be sort of reduced to the previous case. So that is L'Hopital's rule. Now we'll do some concrete examples that will clarify how this thing works as soon as I clean this board. Okay, example 1. We're going to consider this limit. Now, first we verify it is a situation we can apply L'Hopital's rule to, because yeah, as x tends towards 1, log tends towards log of 1, which is just going to be 0, and the bottom just tends towards 0, so it's 0 over 0, so 0 over 0 form. Okay, so one of the things I want you to do is to not start to use this like a black box, that whenever you see 0 over 0, you start to differentiate and calculate. I don't want you to start applying an algorithm before you think about what the question means and turn it into pictures, because in many cases you're going to know what the answer is just from your more elementary reasons, just from understanding the nature of the functions you're looking at. Okay, and so let's do that before we do any calculations. Now, emphasize this really strongly because, again, calculus is taught badly in many places as simply a recipe, a collection of recipes that you apply to various kinds of problems, where you just learn the recipe, which is doing step 1, step 2, step 3, and get to some answer. And that's not a useful thing to learn to do. And it's also not going to help your overall understanding, which is actually the point of this. You're here to learn and understand this language, not to memorize a bunch of recipes without any understanding of them. So not only is this the general purpose for your education, but it's also going to help you for doing exams, because years of experience shows me that's the kind of stuff I'm seeing. I'm seeing people applying algorithms without thinking about the stuff that they're actually trying to understand, trying to compute, trying to calculate, just performing steps and coming up with nonsensical things that if they ever stop to think, what does the stuff I'm writing down mean, they would not be doing those steps. They would not be writing this. The only way they're doing that, the only possibility for them writing these things that they're writing, is if they are not engaging with the meaning at all. Right? And that's what you want to avoid. So if you can visualize this and get some idea what the answer is before you do the calculation, and then what you think the answer is verified by the calculation, then you're in good shape. Then you've got it right. So the multiple choice is merciless when it comes to making small errors. So doing it this way is not only for your long-term benefit, but it's also going to help you in all the subsequent math exams you do. So trust me on this. Follow me with this. Do this kind of stuff that I'm about to do. All right, so let's draw a picture of the situation we have here. We have the graph of log. You have to be comfortable with these elementary functions at this point, as I've emphasized many times. If you're not, then close that gap as soon as possible. So this is what log is. This is 1, right? And if we take x to be a little bit bigger, this is x right here, yeah? And then log of x is this quantity right here. So this is log of x right here. So we are comparing this quantity right here to this quantity right here as x goes towards 1. And the way I've drawn it, it looks kind of like they're comparable, right? They're both going to 0. They are both getting smaller, of course. I mean, x minus 1 is getting smaller, and log is getting smaller. And they look kind of similar. So if we zoom in on this picture, what is zooming in means? It means in the language of math that we're actually going to take a tangent line, right? So we take a tangent line, which we can do. It's a differentiable function. Then we know that log looks an awful lot like its tangent line. And what's its tangent line? The tangent line is something which has got its slope determined by the derivative of log at 1. Derivative of log is 1 over x at 1, therefore the slope is 1. So it really looks a lot like this. Yeah. So as we get closer and closer in, yeah, to the tangent line taken at x equals 1, yeah, this comparison of log x and 1 minus x is more and more like the comparison of the tangent line at x and 1 minus x. Yeah. And you could actually compute the tangent line and stick that in, right? But we're trying to avoid computing things more than we have to. We kind of have a lot of what we need right here. This looks an awful lot from this picture that the limit we should have is 1, right? So that's what we expect from this picture. That's what we think we should get. And then we compute. So this thing, call this star. Star is what we have when we differentiate the top and the bottom. The limit as x tends to 1, differentiating the top is this, differentiating the bottom is this, yeah, and then sure enough it's 1. Good, so it gets to what we expected it to be in any case. And if we think a bit more about this kind of reasoning, what are we comparing? We're comparing this quantity to this quantity, right? And if we look at this, log of x is the same as log of x minus log of 1, because log of 1 is just 0. So actually, star is also equal to this thing. Oops, I should say star is equal to the limit of this thing as x tends to 1. So star equals the limit as x tends to 1 of this expression. And this you should recognize as just the derivative of log at 1, right? Which is just equal to 1. Because again, the derivative of log is 1 over x. So at 1, it's equal to 1 itself. And all this thing is just looking at this, expressing what we see in this picture a bit more carefully. You know? So from this picture, the fact that you can get this just from the fact that this is the derivative of log at 1 isn't a big jump, right? If you're comfortable with what derivatives are, then this to this is not a big jump. So there's another way, and this time this is a fully mathematically complete reason why this thing is also got this answer. Cool. So we are happy with this. We have this, right? If this was a multiple choice, we would now be absolutely certain that we had 8 points in the bank, right? Cool. Let's do another one. Example 2. The limit x tends to infinity, e to the x over x squared. So, what is this? Well, the same strategy as before. We are going to try and visualize this before we do anything else, right? So we are comparing this fight between e to the x, as x goes to infinity, and x squared, again, as x goes to infinity, goes to infinity. And e to the x is this function that grows incredibly quickly, right? Yeah. And x squared There's a quadratic function which also grows fast. X squared kind of looks like this. It's really not a very good X squared. Okay, forgive my X squared graph here. Okay, so the way I've drawn it, it's looking like e to the x is growing faster than x squared, and indeed I drew it that way because I know that is the case, because e to the x kills everything. E to the x is the fastest growing elementary function that we have. Right? E to the x is going so fast, it is hard for us as humans to comprehend it. Many things in the world are the way they are because of e to the x growing so fast. Right? When I talked about this, I talked about how Einstein said that this was the seventh wonder of the world, and that compound interest, there's a saying that compound interest is for people who understand it, they earn from it, and people who don't understand it, pay it. Because it's easy to not understand it. There are many other examples of nefarious usage of the exponential function to essentially defraud people of their money if they don't have enough math background to understand exactly how fast it's going. And it's an easy thing to exploit, though. It's easy to exploit the non-mathematically literate because it's counterintuitive how fast it grows. So just, if you get nothing else from this particular video, at least re-emphasize. I want to re-emphasize that e to the x grows very, very fast. And just as a little kind of toy to play with, what is e? E is like 2.71 something something something, right? So dot. So if we consider for say x bigger than or equal to 1, then e to the x is going to be bigger than 2 to the x. For x bigger than or equal to 1. And let's just, I can't even graph it because it grows too fast, but let's just make a little kind of table of what happens when we play with 2 to the x. So let's do 1. So 2 to the 1 is 1, 2, it's 4. 3, it's 8. 4, it's 16. 5, it's 32. 6, it's 64. 7, 1, 2, 8. 8, 2, 5, 6. 9, 5, 1, 2. 10, 1024. 11, 2048. 12, 4096. Right? Let's just stop there. So, just at 12 already, what slope do we have? So, if this over here is 12, then the value of e to the x is bigger than the value of 2 to the x, which is already 4,000, right? 4,096. So just approximating 4,096 over 12 by 4,000 over 10, that means that the slope here is like the slope of 400, right? So if I was going to draw something with a slope of 400, I'd have to go so much higher. I'd have to draw it way above this, the roof of this house. It'd look almost like a vertical line, right? If this is 12 and I'm trying to sketch 400. So that is how incredibly, it wouldn't be a lot steeper than that. Like this. That is how high a slope we have from the secant line from 0 to 12, 4,096. So that is how fast the exponential function grows. It is insanely fast growing. Whereas 12 squared, what's that? That is 120 plus 24, so that's 144, right? So 144 is a lot less than 4,096, right? So it's not even close. E to the x massacres the quadratic function, and it massacres any other power I can put here. It is fast growing beyond what can easily be understood. So we know for sure this is going to be infinity. You know? So we know this is going to be infinity, but now let's apply L'Hopital's rule. So solution. This thing star. So limit as x tends to infinity, e to the x over 2x. That doesn't look too promising because again it's infinity over infinity, but let's do it again. Let's differentiate it again. E to the x over 2. And then we know for sure that's infinity. Okay, another way to somehow, well, actually, let's save that explanation for the next example. Let's do the next example. Example 3. Consider this. All right, so again, let's call this thing star. And again, we want to get some kind of understanding of what this looks like before we actually apply L'Hopital's rule. So log is the inverse of E. It looks like this. Yeah? So e to the log x is equal to x, which means that log unwraps e. So e sends numbers close to infinity to numbers close to infinity, so log has to do the same thing. However, if we take x and apply e to it, then we're going to get something way bigger than x. Yeah? And then log has to unwrap that, right? So log of x has to be way smaller than x, yeah, for large x. Yeah? It has to be as so much smaller as to unwrap the fact that e to the x is so much larger, right? Which means that log of x is growing incredibly slowly in order to achieve that. In fact, it's the slowest growing function that we have, right, in elementary math. So log is going to be more slowly growing than any other thing you can naturally come up with because it's unwrapping the fastest growing thing that we have. Right? So our guess based on that would be that log is going to grow more slowly to infinity than square root of x, even though the square root of x, so this is log right here, also grows seemingly somewhat slowly towards infinity because square root of x is doing something like this, right? It's getting flatter and flatter and flatter. Now let's try and express that a little bit more. So we know that the derivative, well, let's try and drill down on that. Derivative of this thing is 1 over x. Right? We know the derivative, I should say, well, this is the square root of x. This is a fact. And we know the derivative of the square root of x is 1 over 2 square root of x. Yeah? And they are both getting smaller as x tends towards infinity. Yeah? But this guy is not getting, is getting smaller, but it's getting smaller at a slower rate than this guy. So for very large x, this is a lot smaller than this thing. Yeah? So if we're trying to compare the quantities of log and square root of x, they start off at around, let's start them off at 1. So they're around the same value, around 1. Log is 0, square root of 1 is 1. Yeah? I imagine these are cars starting at more or less the same position. Yeah? And then we let them go. Let them go with their velocity. So the velocity of log is like this. So it starts off at speed 1 and it goes slower and slower and slower and slower and slower. And this guy starts off at speed 1/2 and it's also going slower, but for very, very large x, it is much less slow than this thing, right? So for very large x, this is a much bigger number than this thing. Yeah? So we expect that the square root function, right, which is the distance of our car started from 0, will actually be a lot further along. Yeah? Which is the same as saying that square root is going to be much, much bigger than log. Yeah? So we would expect from that reasoning as well that this thing should be tending to 0. And note, what did we do? We tried to understand the fight between log of x and square root of x by looking at their derivatives and comparing the way their derivatives behave in the limit, right? And that's exactly the statement of L'Hopital's rule. So what we did with the little argument is a kind of micro L'Hopital's rule type of argument. Yeah. So L'Hopital's rule is in fact not an unnatural thing to consider. If you make this metaphor of cars and you're trying to understand how far away they are by comparing that they start more or less at the same place and you're looking at their velocities, then what you're actually doing is an argument that is very much like the explanation for L'Hopital's rule. All right, cool. So with this in mind, with that we expect the answer to be 0, let's actually compute it. So solution star, I'm going to differentiate top and bottom. I have 1 over x here, and then here we're going to have 1 over 2 square root of x. I'm going to multiply top and bottom by 2 square root of x. I'm going to have, this is the limit, x tends to infinity of 2 square root of x over x, which is a limit as x tends to infinity of 2 over square root of x, which is just equal to 0. Cool. All right, so that answer is confirming what we were pretty sure was true in any case. Let's do another example. Our final example of this kind. Example. The limit as x tends to 0 of tan of x minus x over x to the 3. Okay, let's try and understand this. Well, in this case, we have more of a problem because we have some idea about tan of x. Yeah. Its tangent line is line y equals x. And x to the 3, we know what it looks like, and what we're trying to compare is this quantity to x to the 3, and that's not so clear to us. Later, we're going to learn something called Taylor expansion, and then this is a way we could understand a quantity like this. But right now, well, later in Calculus 2, which I hope you all do, right now we don't have the tools to do this. We don't have any picture that's helping us, unfortunately. We look for one, but we don't have one. So we are going to have to do the computation, and we're going to have to be careful with it. We have no backup to give us an alternative answer. All right, let's do it. So let's call this thing star. Star. I'm going to differentiate the top and the bottom. We're going to have sec squared of x minus 1 over 3x squared. All right, as x tends to 0, sec is 1 over cosine, so this thing is tending to 1, so 1 minus 1, and this thing is tending to 0, so it's 0 over 0 again, and that's no good, right? That's again something which we can't just read off. We're going to have to either look at the pictures or just calculate this again. And cutting to the chase, looking at the pictures again doesn't help us too much. So we're going to have to differentiate again. So that's what we do. Let me create some space. So I'm going to apply the chain rule. The outer function is squared. So we have 2 sec of x And then if we differentiate sec, we get sec tan. So we're going to have another power of sec, right? So we have sec squared tan of x. The 1 disappears, and on the bottom here, I'm going to have just 6x. Yeah? Cool. All right. Now, again, as x tends to 0, I'm going to have 0 on the top and 0 on the bottom. Sec tending towards 1, tan is going towards 0. I could differentiate again, but this time I start to see that there's stuff that I can use without having to compute anymore. And I don't want to differentiate something like this because it's got essentially 3 terms here. I just don't want to deal with it. I want to do any more calculation than I absolutely have to. So what am I going to do? Let's write out what sec and tan are. So sec is 1 over cosine, so we're going to have 2, and tan is sine over cosine, so 2 sine. And on the bottom here, we're going to have a cosine squared from the sec squared and another cosine from the tan. So we're going to have cosine to the power 3 of x times 6. Let's just get rid of this 6 and 2 and replace it by 3 on the bottom. And not forget the x. Okay, so once we look at that, then it looks kind of simpler, right? And now you should be looking at that going, okay, well, as x goes towards 0, this cosine is just going towards 1. It's kind of a benign thing. It's not really affecting things too much, right? So the real meat of this is what is happening with the sine and the x, right? And that should strike a memory for you that that's something we understand. We know this limit, x tends to 0 of sine of x over x. It's just equal to 1. And that was just this picture here where we compared this little straight line part here, which was sine of x, where x is this angle, with the little bit of the arc given by this. And they are both going to 0, and they're both going to 0, but they're looking incredibly similar to each other. So when we consider the ratio of the two of them, they actually tend to 1, right? Because the length of this little opposite side of the triangle and this little arc here is incredibly close to each other as we let the angle get smaller and smaller. So we know the limit of sine of x over x. So let's break this thing up into 1 over 3, 1 over cosine to the power 3 of x, and then sine of x over x. And if we do that, what happens? Well, as x tends to 0, again, this thing is just tending towards 1. And this thing is tending towards 1 itself. So what we're looking at here is a product of things, each one of which we know the limit of, right? And the limit is non-zero. Well, actually, it doesn't matter because it's just a product. We have a product of things, each one of which we know the limit of. And then we can just, I haven't written the limit signs here. That's a very bad thing to have done. This is the limit as x tends to 0. This guy is the limit as x tends to 0. This is the limit as x tends to 0. So we can apply the product rule for limits. So it's going to be 1 over 3, the limit as x tends to 0 of 1 over cosine to the power 3, and then this limit as x tends to 0, sine of x over x. And that's just going to be 1 over 3, because everything, this is 1, so it's 1 times 1 times 1 over 3. And that's our answer. Cool. All right, so that is how we do the most basic kind of L'Hopital's rule application when we have something of a form 0 over 0, infinity over infinity. Now we're going to learn how to do more subtle applications when we have to consider indeterminate products and indeterminate powers. And this looks like a much harder task, but I'm going to show you that it's actually not that much harder. All right, coming up. Okay, indeterminate products. Product. I don't know how to spell that word. Product. Okay. Indeterminate product. So suppose we have that the limit as x tends to a, f of x is equal to infinity, and the limit as x tends to a, g of x equals 0. Then if we want to consider this thing, x tends to a, f of x over g of x, it's again a fight. It's a fight between how fast this guy goes to infinity compared to how fast this thing goes to 0. Yeah? And we can turn it into the kind of situation we know by either writing this, yeah, or by writing this. Because in this situation, because g of x is tending to 0, this will be infinity over infinity form. And since f of x is tending to infinity, this will be 0 over 0 form. So it's just a matter of differentiating 1 over g or 1 over f, whichever seems to be the easiest thing to do. That is not a hard situation to deal with. So we're not going to have an example of this because, 1, it's not particularly hard. And 2, we're also going to see this when we do the next thing, which is the most important thing, or at least the trickier thing, which is indeterminate powers. So indeterminate products is just applying this trick. You'll have examples in the practice homework, definitely do them. You'll have examples on the homework, obviously do them too. Now, indeterminate powers. And I know how to spell powers. So that's when we have a situation like this. We're going to have, well, okay, so we want to know, let me phrase it a different way. We want to know something like this. The limit as x tends to a, f of x to the power g of x. And we have various possibilities where, for example, the limit as x tends to a of g of x, let's start with f of x, where the limit of x tends to a, f of x is equal to 0, and the limit as x tends to a, g of x equals 0 as well. That is the 0 over 0 form. So why is this a fight? Well, it depends again at the speed at which these guys tend to 0. So if we have a number which is going very slowly to 0 and we take a very, very tiny root of it. So imagine we have a number which is like small, like 1 over 10, and we take the 1,000th root of it, right? So 1 over 10 to the 1 over 1,000, okay? And suppose that thing is x, yeah? That means that x to the 1,000 is equal to 1 over 10. That means x is going to have to be very, very close to 1. It's less than 1, but very close to 1, or there's no way that could be true, right? If we had, for example, 0.9 to the power of 1,000, it's probably going to be a lot, well, for sure, it's going to be a lot smaller than 1 over 10, right? So hopefully you're getting happier and happier with the graph of root powers, but the smaller the root power, the more flat it looks like this. Obviously at 1, it's 1, right? It looks more and more kind of like this as we take smaller and smaller roots, yeah? So if in this battle we have that f is tending more slowly to 0 than g is, then we expect this thing to be something like 1. Conversely, if f is going much faster to 0 than g, if we have 1 over a million, and we take the 10th root of that, that's still a pretty small number, right? So this thing is really unclear from the situation. It's a battle between these relative speeds that these guys go to the limit. It's in the territory of L'Hopital's rule, right? And other situations we can have where the limit as x tends to a, f of x is equal to what other one do we have? We have the limit where this guy is 1 and this guy x tends to infinity, g of x equals infinity. This is 1 to the infinity form. Again, a battle. If we are sufficiently close to 1, then taking a very, very high power is not going to change things much, right? On the other hand, if we're not that close to 1, if we are 1.1 and we take it to the power 1,000,000, then that's a pretty big number. It's a very big number. Yeah? So again, a battle. Final situation for limit as x goes to a. I think it's 0 to the infinity, but let me check. Infinity to the 0. F of x equals infinity, and the limit x tends to infinity, g of x equals 0. Again, a battle. So infinity to the 0 form. If we are going fast enough to infinity, then we're going to actually have infinity. If we're going faster than this guy's going to 0. Conversely, if this guy's going closer to 0, faster to 0 than this guy, then it gets closer and closer to 1. Yeah? If we have 1,000 to the 1 over 1,000,000th root, then that thing has got to be pretty close to 1. So again, a battle. So in any of these three situations, we have a battle about which guy gets to which thing first. And this thing seems to be quite intimidating to students, and I see why it was to me back in the day. But we have this really powerful trick, essentially, of avoiding talking about things that are powers of functions by taking the log. And we saw this in log differentiation. Whenever you see some function to the power of another function, just think, okay, I don't want to deal with it. I'm going to log the thing, and then I'm going to unwrap whatever I understand with an e at the end, because log and e are the inverse of each other. So this is what we do. So we say, suppose this thing is star. Or let me say it like this. Let's write h of x. Let's define it to be log of this weird thing that we're trying to understand. Oops. Like this. Yeah? And by log rules, this is g of x log of f of x. And now this will be an indeterminate product that we can actually analyze. So by L'Hopital, we can figure out what this thing is, that the limit as x tends to whatever limit a h of x, we're going to be able to figure this out. Say it's L. And then we can understand the thing we actually want, which is this thing, star, is going to be the limit as x tends to a. Now, this guy, f of x, the g of x, is nothing but e to the h of x, because that's what h is defined as, right? And we know that e is a continuous function, right? So we learned about composing continuous functions and passing the limit through the outer function. Go back, if you're unfamiliar with this, it was just, we had these two graphs, and it was just seeing what happens as we went from one graph to the next graph in the limit, right? So if we do that, then this is just equal to e to the limit as x tends to a, h of x, which is just e to the L. If you're doing a free response, do not just write e to the L. In fact, just don't get in the habit of just writing e to the L at all, because this step's important. Don't start to backwards engineer an algorithm from the explanation. Understand why this makes sense. Understand why we have the right to do this. But we do have the right to do this for the reasons I said, and therefore we do have an answer once we can find the limit of h. And h, again, is just going to be an indeterminate product, something we can actually answer. So let's do the first example. Let's try and find the limit as x goes to 0 plus of x to the power x. Okay. Solution, no pictures here, nothing to help us. We just have to use the tool. So, well, of course, there are pictures, but there's no pictures I can draw for you that's going to help with the stuff that we've already learned about calculus. So we are just going to have to use our tool. So we're going to let h of x equal log of x to the power x. Yeah, which is x log of x. And now it's an indeterminate product because as x is going to 0, this is 0 times infinity, right? So I'm going to write this as log of x of 1 over x, and I'm going to differentiate to actually find this limit. One over x over minus 1 over x squared. I'm going to multiply top and bottom by x squared. So the limit as x goes to 0 plus, should have put the plus, of minus x, and all that is 0. So we're all good for finding the limit of h. Now, an easy mistake to make is to think, okay, I've just found the limit, that's the answer. And in the multiple choice, they will try and trick you by having the answer for what the limit of h is as one of the possible answers. So don't get tricked. We are not finished. We've just found the limit of h, but we're looking for the limit of this thing, which is e to the h. So, did I call it star already? No, I didn't. Okay, let's just rewrite it. Limit as x goes to 0 plus x to the x is going to be the limit x goes to 0 of e to the h of x, limit as, oops, I'm passing it through the e, so it's going to be just e to the limit as x goes to 0 plus of h, and we've worked that out already, it's just 0, right? So it's just e to the 0, which is 1. So we have our answer. And it's not much harder than just doing standard L'Hopital's rule, right? All we had to do in addition was just this, make it, just use log to turn it into a product, and then do L'Hopital, and then use e to unwrap what we've got. Okay, let's see if we can squeeze in a final example. This guy. Example. Limit. Let's go to 0's plus 1 plus sine of 4x cot of x. Okay, let's call this thing star. And we're going to do the same thing. So we're going to do h of x is log of this thing, which will be cot. So I know cot is just 1 over 10, so let's write that straight away. So it's going to be log of 1 plus sine, because we're running out of board space, over tan of x. Okay, and as x tends to 0, we're having 0 over 0 form, because this guy is going to 0, log of 1 of 0, log of 1 is 0, and limit as x goes to 0 of tan is 0. So it's 0 over 0 form, so I'm going to differentiate both sides. So limit as x tends to 0 of h of x differentiate this guy. So we're going to have 4 cosine 4 of x, differentiating the inner function over this thing here, because we're applying the chain rule. And the outer function is log, whose derivative is 1 over x. So that's differentiating the top. And this is over tan. When we differentiate it, it's going to be sec squared. Oops, and I forgot the limit signs, which is an error I make a lot. Limit as x tends to 0 plus. Okay, cool. And now we are happy because the limit on the bottom is just going to be 1 because sec squared is just 1 over cosine squared. The limit of the top, this is a quotient as well. And this guy is just tending to just a 1 on the top because then we get limit of cosine 4x as x tends to 0 is 1. And the limit of the bottom is tending to 1 because sine of 4x is tending to just 0. So this is just going to be 4 over 1, which is just 4. I'm going pretty fast, but running out of space. Okay, so this limit we understand. Now we unwrap. So star equals the limit as x tends to 0 plus of e to the h of x, which is equal to e, the limit as x tends to 0 plus h of x, which is equal to e, and we found out what this thing is. It's e to the 4, and that's it. Cool. So, not too difficult, right? So, do not be intimidated by things like this. If you can do L'Hopital's rule for ordinary 0 over 0 form or infinity over infinity, you can also do this. It's just one extra subtlety you have to handle. And all you have to remember is to take the log, and then it's natural what you do. Once you've understood the limit of the log of that thing, then to get back to the answer you want, you're going to apply the e. So you only have one thing to remember, and then you just do the natural common sense thing. So don't be intimidated. Many of you, or some of you, will not have seen this before. This isn't a particularly hard thing to do. Practice it, and you'll feel fine with it. All right, that is the last thing we need before the midterm. Get good at this, and that's all the things that we examined, all the topics since the last midterm. As I said before in class lots of times, do the practice exam. Do it inside out, know it backwards. Do the 2 posted past exams. Focus on your weaknesses. Do the preparation. What you do in the exam is just a function of your preparation, or is 90% a function of your preparation. And if you've put in the preparation, it'll go fine. And if you haven't, it will not. So do the preparation, and good luck to all of you on the exam. All right, have a great weekend.